My name is Ahmed Hammad, and I'm from the Theory Center, KK in Japan. And I'm going to discuss about multi-scale cross-attention transformer encoder for event classification. The topic, my talk has two main parts: the formulation of the multi-scale transformer network, and in this I'm going to discuss the main mechanism of any transformer network, which is the attention mechanism. And I'm going to discuss a bit about the two basic types of the attention, which is the solve attention and the cross attention. And I'm also discuss why the cross attention is important if we have two different scale of information that we want to analyze. The second part, I'm going to discuss about interpretable methods. And as obviously known that the transformer network is a very complicated network that has lots of tunable parameters, and it does lots of matrix multiplication. So we need interpretable methods to explain the results of the network. Otherwise, maybe there are lots of mistakes comes in during the numerics flow by mistake. And for those, I'm going to discuss about the attention maps and the gradient weighted class activating map, which in short is a Grad-CAM. Okay, so I just start with the at any event at any particle collider, it has two kind of information: the global information and the local information. So the global information actually it span the full phase space, and it gives us a generic information about the events itself. And those it can be reconstructed from the final state particle of the kinematics of the final state particles, like momentum, mass, holistic correlation, etc., etc. For the local information, are those information that are localized inside a specific part of the collider. And here I'm talking specifically about the jet constituents, which localize the information about the jet into the radius of the jet, like here. So having the information about the final state particle, like for example, two electrons and two jets, then we can have more information about the events in general. But having information about the hadrons inside jet, this can give us information about the properties of the reconstructed jet. Well, so we can use those information separately for any classification problem, like for new physics, for example, search. So we can include the kinematics of the new physics, and also for the background, just the distributions, feed them to a neural network, and then you could have the classification. Also similar for the local information, which is about the jet substructure, for example. And in this case, this is a classification between the top jet and QCD, where we utilize or they use the multi-prong structure of the top jets to distinguish it from the QCD jet, which doesn't have any prong structure. So we can use this two information, feed them for a network, and then we could have the classification. But the idea here is that if we want to really improve the classification performance of the network, then we need to use both information at the same time. Like to have all information, all possible information about the signal, such that the network can easily identify it from the background events. So one easy, straightforward way is to have a multi-modal network where the first network, it analyzed the global information, the second network analyzed local information, and at the end, it concatenates the output of the two networks. And then we pass them to a fully connected layer to make the classification between the signal background. The point here is that the global feature, actually, it has a more discriminative power over the global feature. And thus, the first network assigns high weights to the outputs than the second network. In this case, we have a concatenation layer with two different weights. Thus, the network will completely focus on the global information and ignore the local information from the jet substructure. In this paper, the author actually highlights this problem, and they do this simple exercise. So they have the 2 Higgs di-Higgs production, and they have the fully connected branch that analyze the high-level kinematics, which include the global information, and the CNN branch that analyze the QCD observables, which include the local information of the two jets. The output is being concatenated to one concatenation layer, and then they compute the attention before they have the output. So the attention here, it represents how important each of the particle tokens or each of the tokens in the two data sets to the classification of the network. And this is what the right-hand side plot highlights. So the x-axis represents the output from the CNN, which include the local information, and the output from the fully connected layer, which include the global information. The color part represents the attention, and the y-axis is the number of the neurons in each of the layers. So as you can see, the model actually has no attention, like a very small attention to the local information, while it highly attend to the global information. That means that the model completely focus on the reconstructed kinematics to distinguish between the signal and background and completely ignore the information from the jet substructure. So the question now is there any better way to incorporate these two information and to make the model use them together? And the answer is yes. We can use a multi-scale transformer network. So the transformer network is first introduced in this very famous paper, Attention is All You Need, which is now over 100,000 citation. And this is the structure of the network. And as you can see, the heart of the transformer is the attention. And the attention actually takes three inputs, like the query, key, and value. So having this example, so we have one sentence. It has a dimension of d times n, where d is the dimension of the number of the words in the sentence, and n is the dimension of each word including. So we reconstruct three tunable matrices: query, key, and value. So you can think of this query, key, and value like if you, for example, if you want to search for some video on YouTube, and then you type the word, this is your query. And then the YouTube return a list of suggested videos. Those are the keys. And the idea here is that the value is how relevant each of the list, which is represented key, matches your query. And this is what exactly this attention tries to do. They try to highlight the important tokens in the query, match the key given some value. And this can be guaranteed by this famous formula. So once we reconstructed the three tunable matrices, then we can multiply the query times the key transpose, and the output can be multiplied by the value. And then we can add the skip connection. The output of the attention has exactly the same dimension as the input. But importantly, the output, it encodes in each element how it's important to the whole data set and also how it's important to the decision for the model. Well, so maybe someone say, okay, it's naively just one data set we multiplied different position, and what does that actually mean? So in this paper, it's about the vision transformer paper. So people highlight this. So here, this is, for example, this is the input, and we want to design a transformer model to identify a dog inside the picture. So after we apply the attention mechanism, the network assign high attention to the dog body, and they ignore everything else. And this is what exactly the attention mechanism does. It assigns high weight to the important tokens and ignore everything else. So this is about the self-attention. So what about the cross-attention? The cross-attention actually, it extends the self-attention by having two different data sets, X and S. So X here, it includes the global information, and S, it includes the local information inside each of the jets. So X here has two dimensions, I, which run over the number of the particles in the event, and J, which runs over the featured of each of these particle tokens. S has two different dimensions, N and M, where N runs over the number of the jet constituents, and M runs over the feature of each of the jet constituents. So having these two inputs, we can construct the query, key, and value matrices. The attention output can be computed similarly, but the point here is that the output from the attention has the same dimension as the input data set, which include the information of the high-level kinematics. From this is actually the attention output for one attention head, but having a high dimension feature space, then we need to use a multi-heads such that each head can capture a different information from a different features. And we can run them for n heads, and we can run them in parallel to speed up. And at the end, we can concatenate. But we have to add a normalizing trainable matrix to preserve the dimension. So after we concatenating all the multi-heads, the dimension still have the same dimension as the input data set for the high-level kinematics. And finally, we add the skip connection, where the output, the attention output, can be added to the original data set, such that the modified or the transformed global information now are weighted with the relevant information extracted from the jet substructure. So this is how is depicted here in this figure. So you can think of the global information as we have the final state particles, and each particle tokens has its features. And we have the other data set here, which is represented by the S, N, and M, where we have the jet constituents and each of the local features. After we perform the attention or the cross attention, the output has the dimension of the particles and also the dimension of the global features. But each of those elements are now weighted with the most important information for extracted from the local information. And this is exactly this is the cartoon to just visualize the difference between a simple concatenation and cross attention. So if we have a simple concatenation, then we have Tom and Jerry, you just combine them. So at the end, you have a one element that has two different scales. So most likely, if you have a network, then it will focus on Tom, ignoring all the information come from Jerry. But if you have a cross attention, then the information from Jerry is extracted and combined to Tom, such that at the end, we have one element in one scale that the network can use very efficiently. Well, so that was about the differences between the cross attention and self attention. How can we use this in high energy physics? So we tried example of the Higgs production from a heavy scalar. So these systems are boosted, so we can reconstruct a Higgs jet from the two bottom quark. And for this, we have two kind of information: the local information, which is included inside each of the Higgs jets, and the global information, which is the information about the high-level kinematics, about the two of these Higgs and the heavy scalar, that include the whole kinematics, the whole information about the event. For this, we reconstruct a transformer network with the three inputs. The first input, it's analyze the leading Higgs jet. The second, it analyzed the subleading jet. And the third input, it analyzed the kinematics. So we use a solve attention with a different repetition number, like a different ends here. We can repeat them many times. So we use different repetition for all of them. And then we concatenate the extracted information from the jets and the high-level kinematics via cross-attention heads. And then we add a MLP before we do the classification. So importantly to see that the signal has a very distinct structure that it has two-pronged structure, like each of those Higgs has a two-pronged structure here, which is highlighted here. While the background from the QCD, it's 90% from the QCD and 10% from the TT bar. So for the QCD, there is no any prong structure at all. For the TT bar, we have like a three-prong structure. So this is a nice feature that we can use as a local information that the model can assist the global information to make a decision. Well, so this is the output. I want to, from this busy slide, I want to highlight only two results here, where the one that we concatenate the jet information and the high-level kinematics via symbol concatenation. And the other one where we just combine the information from the jets and the kinematics via cross-attention. And as you can see, there's almost 4% improvement, which is a really, really big margin. So this is actually highlights why it's really important to use the cross-attention in case we combine two different scales of information. Well, so that's good results. But what exactly next? So next is the interpretability. But before we go to the interpretable methods, we just ask, why do we need to use interpretation methods? Well, so this is the network that we show in the paper, but actually this is how it looks like. So you can see it has this very complicated structure, and this is the actual network that we use. So it's really, really dangerous to use such a complicated structure as a black box. And we need to explain the decision of the network. So for this, we use the attention maps. And the attention maps is a visualization interpretation method that highlights the particle tokens that receive high attention scores, indicating their significance in the model decision. So here we use a 5 attention heads separately, which has been represented for the signal by the upper row, and the lower row represents the background events. So as you can see, the particle tokens for the signal, the model focus on the first few or even the first and second particle tokens for the signal in most of the attention heads, while for the background, the model actually span its attention to a large number of the particle tokens. So why that? That's because the substructure of the signal, it has only two prongs. And those two prongs come from each of the two B quarks here. But for the background, which is really dominated by the QCD, there is no prong structure at all. And this is how this attention map reflects. So now we guarantee that the self-attention part and the network capture the physics of the jet substructure. Now, what about the cross-attention? For the cross-attention, it's actually combined two different information, like the global information and the local information. And this is what we highlight here. For the upper plot, the attention of the signal, and for the lower plot, it highlights the attention for the background. So in the y-axis, we have the three reconstructed final state particle, like the leading Higgs jet, second leading Higgs jet, and the heavy scalar. On the y-axis. On the x-axis, we have the jet constitutors. So as you can see, the first and second leading Higgs jets, they show high attention to the first few jet constituents. And also, the heavy scalar also show really high attention to the first few jet constituents. And that reflected the bottom level information that if we have bottom level information about the B quark, not at the jet level, but the B quark, the highest momentum for B quarks, then we can have the information about the heavy scalar, or reconstruct the information about the heavy scalar. But for the QCD, or for the background, this correlation does not exist at all. So now we know that the cross-attention also capture the information of the bottom level or the process at the bottom level, highlight this relevance between the jet substructure and the high-level kinematics. So now with the attention maps, we visualize what are the important particle tokens that the model highlights to make a decision for classification between the signal and background. But what about the feature space? Well, so to highlight the important part of the feature space, like for example, momentum, mass, etc., then we need to use a Grad-CAM. So Grad-CAM has been first introduced for the CNN model to visualize the most important pixels in the image for the model to make a decision. So for example, consider this image that it contains a cat and dog. If the model classified this image as a cat inside, then the model will focus on this part of the feature space. And if the model classified this image as a dog inside, then it will mostly focus on the face of the dog. So this has been first introduced for the CNN network, but we just modify this one to use it in our transformer network by just modifying the feature space. Well, so as a result, here we show the original feature space of the signal jet and the original feature space of the background jet, and we show the Grad-CAM results. So for the Grad-CAM results, the model mostly focus on the middle part for the signal, which somehow recognize exactly this two-prong structure. While for the background, the model actually vary a lot and they cannot capture any prong structure at all. So with these two interpretation methods, we know exactly what are the parts in the particle token space and the feature token space that the model use to make his decision. And actually, this is very important. Otherwise, as I show you, the numeric flow may make some bad decision or mistakes inside. And the main problem in that, especially in this kind of complicated network, that if you do a mistake in preparing your data set or you do a mistake in the training or the test, you will get a pretty good result. And this is really dangerous. So we need to use interpretation methods if we use a complicated structured network. Well, so finally, our code is for public and it's very, very generic and it can use for different purpose. And you can run it with a very simple command in the shell, in the terminal, just Python 3 run.py your input. And this input file, it contains all the information and all the needed and all the command and the structure from your own. So let me go through it very quickly if I have like 5 minutes or 3 minutes remaining. So in that network, we provide here a 3 structure of the transformer. The first one is that only one transformer model that analyze only one data set. And also we provide a second network that can analyze 2 data sets. And at the end, it combine them with the cross attention. And also we provide a third model that it can take 3 input data sets. So what you need in your computer is TensorFlow, scikit-learn, and NumPy. And to run it, it's pretty easy. You just Python and run.py, and then you have your input.py. So what exactly is input.py? So input.py here, it contains where in this input file, you can control the structure of the network from bottom to top. So here you can decide what exactly the model that you want to use, which is structure, the number of the events, like the whole number of events, and you also have to decide the test ratio, if you want to use attention mask or not, the number of the classes, like if you have a multi-class classification problem, not only 2, also the batch size that you want to use, the number of epochs, number of the MLP units, dropout rate, learning rate, and if you want to compute the curve or not. The point here is that this input file, it contains a blocks. And if you, for example, want to use the first model, then the network will only focus on this part here. So what you have to specify, the signal events and the background events. the number of the heads that you want to have, and also the number of the hidden dimension. And this is the number of the hidden dimension is this, I can quickly show you, sorry, is this number here, the second number of the matrix, this M here, and this J here. So you can increase this number for more expressive power of your network, and how many times you want to repeat your transformer layer. And also you have to give the structure of your input, like the number of the constituents and also the number of the feature space. If you wanted to use, for example, the second or the third network, then the network will focus on this part. And in that case, the network takes two inputs, and you have to specify two inputs for the signal, two inputs for the background, and also the number of the heads of the self-attention head for each of the branch, and the number of the heads or the information about the cross-attention that you have to specify here. Like how many heads you want to use in the cross-attention layer, and the number of the cross-attention that you want to use. Finally, I want to, in 1 minute, I want to highlight that we have also demo version that you can run very easy by just running this command. So after you just download the data, then you can write down this command, and it will process for you the data that is stored in here for the signal background. And I want to notify that you can easily modify the network going here in the structure of the network. So you can find here, this is how we define the self-attention encoder network. And this is how where we define the structure of the cross-attention network. And this is like the basic command in the TensorFlow. So you can easily modify, add, or do whatever you want. Like you increase also the number of the inputs, like from left to right. You can also do it here. Yes, so that's all about this, and thank you.
Yeah, thanks a lot for an interesting presentation. Yeah, I think we have time for 1 or 2 short questions. Are there any questions to Ahmed? Maybe I have a quick one sort of on the implementation of this. So I mean, it seems like from what you have shown, it's very specialized to your specific data set. So if I would want to apply this method to my custom data, what would I have to do? Is it sort of modular that I could also have sort of a custom data loading procedure? Or,
Yeah, so
what would be the steps?
Yeah, perfect. So what you have, thank you for this question. So what you have to do is just you change, of course, you have to change the number of constituents over here and the number of the feature space. So it's always the transformer networks. It's worked for particle cloud data sets, right? So in that case, you always have the particle constituents and the relevant features on top of that. So you could have a different dimension of your data. So what you wanted to do is just you have your data in a grid, and then you have to give here the network, the structure or the processing structure of your input data, and you can also control everything else. But the part that the network is looking for is this format. So whatever you have, then your data, you need to store them in MBZ format, such that the model understand them. Otherwise, you can easily change the data loading, and in that case, you can change them here. So here, for example, this is how we load, and when we run. So this is how we load the data for the signal and for the background. So whatever the format of the data that you store, you can easily change here how you want to load them.
Okay, yeah, so it means essentially like looking at this, one requirement would be, for example, that I can load the full data in memory.
Ah, hold it in a memory. No. Yeah, actually, no. At the moment, you just have to have your data on the disk, and then you have to load them.
Okay.
Yes. So this is the yeah.
Since this is a NumPy array, it could potentially be a memory mapped array.
Sorry, can I
But
say again?
I have to make a copy of it or transform it or something. Then it would be in memory.
Right.